All right, everyone. Welcome to the third seminar of our winter Colloquium. Just a quick announcement that we had a change in the schedule of the speakers. So please go ahead and encourage everyone to check out the latest updated schedule of the talks on our website, on the UW-ECE website. And for today's talk, we are actually honored to have Dr. Shimeng as our speaker. Dr. Shimeng is an associate professor of ECE from Georgia Tech. He's been doing many pioneering work in emerging memory technologies and compute in memory, basically system implementations for kind of new applications of AI and ML. He's the recipient of many awards, including the prestigious NSF and SRC Early Career Awards. And with that, please virtually welcome Dr. Shimeng and you can take it away from here.
Thank you, Sajid. First of all, thank the Department of ECE from University of Washington, Seattle for inviting me to this colloquium here. And it's my great pleasure to share some of our research progress on the circuit design and silicon prototyping efforts for the computing memory, which is a new compute paradigm for hardware accelerations of the emerging workloads such as deep learning inference. So today's presentation, actually we had most of the materials covered from this invited review recently, and which is appeared at IEEE Circuit and System magazine. All right, with this, I'd like to get started. So this would be the outline for today's presentation. First of all, I will give a background of this computing memory, which is a kind of new computing paradigm for accelerating some of those data-intensive workloads. And then we will give some survey of the recent computing memory prototypes with SRAM technology. Those have been implemented in the silicon. And then we will switch the topic to some of the emerging technologies. And in this particular case, we're going to discuss the resistive random access memory-based design, or RRAM for short. And then we will discuss some of the general design challenges if we want to implement the hardware using this new architecture. And then lastly, I will point out some of the future directions to pursue, which could be the monolithic 3D integration for the chip design. And finally, I will summarize and give an outlook. So first of all, there is a huge interest in the community to develop the hardware accelerators for the AI applications. And here we show different platforms today for the AI hardware acceleration. And of course, a GPU, as you may be familiar with, is very powerful in doing those machine learning workloads. And we still say that GPU dominates the training workloads, especially in the cloud environment. But we see more and more inference engines designed to use FPGA, especially for the edge applications, and especially when you want to change your algorithm and you can have some faster prototyping with FPGA. And the other emerging trend is that the companies are designing their own custom silicon chips using the digital CMOS ASIC solutions, such as the TPU, tensor processing unit. This is one representative hardware accelerator designed by Google. So if you look at today's available platforms, you can look at the one metric here, that is energy efficiency. And so here we quote the number for the TOPS per watt. Essentially, this is throughput divided by power. And for today's conventional computing platforms like GPU, FPGA, the best one could reach about 0.1 TOPS per watt. For example, the GPU from NVIDIA these days. And also this could accommodate a floating point computation for very high accuracy. And then the digital CMOS ASIC design typically employ lower precision fixed point computation to boost the efficiency and also try to optimize the data flow to reuse the data more efficiently on chip, and therefore it can boost the energy efficiency to about like 1 to 10 TOPS per watt. And here in today's talk, we're going to discuss something beyond the conventional paradigm, and here we call it computing memory. So here the idea is to embed the computation directly into the memory array. And we expect to use some of the analog computation techniques to boost the energy efficiency further to like 10 to 100 TOPS per watt. Of course, we are going to try to use some low precision techniques, and therefore you may have a doubt whether this low precision analog compute can achieve similar accuracy as a digital counterpart or not. And we are going to address some of those challenges later in today's talk as well. But here the key idea is that we try to embed the computation into the memory array. Therefore, we don't need to move the data around. We can reduce the data traffic on chip. Therefore, we can improve the energy efficiency. And we would envision the analog approach coupled with computing memory, possibly with some of those non-volatile memories we're going to discuss later today, could be a promising solution, especially for the edge inference, where the standby could be often, like your edge devices. In most of the time, then it's in the sleep mode. Therefore, we may wish to reduce the standby leakage for the edge applications to improve the battery lifetime for those sensor loads. And in the future, we envision that we could also do some transfer learning with the possibly unlabeled data sets for those edge chips as well. But the initial target should be the inference only. And then let's take a closer look at the computing memory paradigm. So actually here we show two architectures. The first one is more like a near memory compute solution. And this is also used in the TPU architecture designed by Google. So the basic idea is to have many of those parallel process elements, or we call PE. So essentially those are the multiplier and adders in the digital circuit. And then there's a shared SRAM as global buffer to store the, for example, the weights or the intermediate data of the neural networks, like the input and output activations. And of course, there could be some specialized units to do the special functions like pooling, activation, and so on. And in many cases, we have to fetch the data from the off-chip DRAM because the capacity of the shared SRAM could be limited to hold all the weights on chip. Therefore, we have to talk to DRAM to get the data as well. But the whole idea here is to minimize the data traffic by reuse the data as much as possible. But still, here the computation is done at this processing element in the digital circuits. The weights and the input and output data still are stored in the SRAM. So here we need to fetch the data from the SRAM buffer to the compute units and then perform the MAC operation, multiply and accumulate, and then save the data back. So still there are quite a lot of traffic in terms of the data transfer. And then here we want to design something beyond this conventional architecture to embed the computation into the memory directly. So here the idea is that we have many of those macros with this computing memory, we call it CNM. And here there are memory arrays. So that means we have the rows and columns, and then we have the memory elements. And then the idea is that we do the MAC operation directly on this memory macro. So here we load in the input in parallel, and then activate multiple rows, and then we do the multiplication inside the memory array, and then do the summation at the end of the column. Therefore, we can get the input and output vector efficiently without moving the data around. So this could enable the parallel computation and improve the throughput as well. So let's take a closer look at one of the subarray for this kind of computing memory architecture. So if you imagine this is one memory subarray with many memory elements. So typically memories are organized in this kind of two-dimensional array format. So you have the rows and the columns. And then here, the idea is that we load in the vector. For example, you input feature map from the neural network in parallel, and then we encode that as a voltage to activate many rows in parallel. And then the element here is a memory cell, and the memory cell will have its own conductance. So if we can have the voltage multiplied by the conductance, then we can get a current from each of those elements. So here, essentially, we're doing the dot product between the input and then the weight we stored in the memory. So here, we get the current, and then we can sum up the current along the column. So naturally, the current has to be added through the column, following the Kirchhoff law. Therefore, at the end of the column, we have the weighted sum current, and this current is proportional to the output vector. And then we can quantize that through the peripheral circuits. Because here this is analog current, we still may wish to have the digital output. Therefore, we may need to use the ADC, analog to digital converter, to convert the analog partial sum to the digital final sum. And then we may need to use some shift and add module. Then imagine the weight precision and the cell precision may have a mismatch. For example, if the algorithm require like 8-bit weights, but your memory cell is like a binary only. For example, if you use SRAM, you can only store 1-bit data in one SRAM element. Therefore, you may need to use 8 SRAM cells to reconstruct the 8-bit weight. So we need to use a shift and add module to reconstruct the significance of the weights from the MSB to the LSB, and then you do the digital shift and add. And then in terms of the memory element in the array, it could be the 6 transistor or even 8 transistor SRAM cell. And this is available in today's CMOS foundry. And we can modify the circuitry to accommodate this kind of computation in parallel. And also we can explore some emerging technologies, and we're going to address that more in details later. For example, we have like a resistor with variable resistance as the weight to encode the multi-bit weight into multi-bit resistance, one multi-level resistance. And then here we can have one transistor, one resistance, one transistor, one resistor, one T1R cell to be more compact than the 6 transistor or even 8 transistor SRAM cell. And we're going to discuss more details of those 2 implementations in the following sections. And this is just an overview to set the stage for today's presentation. All right, so let's look at the first implementation of this kind of memory compute in memory prototypes with the SRAM technology. So first of all, why SRAM for computing memory? Because SRAM is widely available in today's CMOS technology, and it's a mature technology that scales well with the logic process, and is available at 5nm process today, and possibly 3nm very soon, as you see the announcement from TSMC and Samsung very soon. And the computing memory require large capacity for those memory arrays. And at 5nm, I believe people have demonstrated 256 megabits SRAM caches already used in today's processor. And we can modify the SRAM to enable the computation. So here we show some variants of the modified bit cell. So if we don't modify anything, we can use a conventional 6 transistor SRAM. So this is like a coupled latch in the middle, and then this is the 2 passgates to access the data stored in the Q and Q bar. And we can enable the computation by activating the VLAN. So let's assume the data pattern we stored here is that Q is 0 and Q bar is 1. So we rely on the current along the column, which is bitLAN, to do the computation. So here, imagine that the input is 1, then we turn on the VLAN, and then depending on the data we stored here, for example, here if we pre-charge the bitLAN to be VDD, and then here, then we will have the VDD and here we have ground. Therefore, we have a discharge current flowing through this cascade transistor. And on the other side, because here, if this is supposed to be 1, then there will be minimal current. Therefore, here we can say that if we have the data stored 0, we will have a discharge current to the bitline. So this is just for one cell. And remember, we activate the arrays in parallel. So there are many of those kind of cells vertically here integrated in one column. So we can count the discharge current from the bitline and the bitline bar, and then decide which one has a lower voltage potential after the discharging. So we can do those activation in parallel. But there would be some challenges. For example, here, if both bitline and bitline bar discharges, then the sense margin could be reduced. And one way to improve the sense margin is to have this split 6 transistor SRAM design. So the key difference is that we use a separate VRLAN to control those two cascades. And we have VRLAN and VRLAN bar. In this case, if we have the input, then we're going to encode that into the VRLAN bar and the VRLAN as well. So in this example, here you see the input. We have the complementary input from the VRLAN and the VRLAN bar. Then we can only discharge the right access transistor, and the left access transistor, because it's controlled by 0 input, this one could be completely turned off. Compared to those two cases, you will see that this one only has the right bitline to be discharged. Therefore, we can improve the sense margin between those two sides. And this 6 transistor SRAM is compact, but it does have one problem. That is rate disturb. Because as we turn on multiple rows, both VRLAN and VRLAN bar could decay. And then if the voltage potential on the bitline is too low, then the data that stores 1 in the storage node could be disturbed. So we want to prevent this kind of rate disturb. So we can add 2 additional cascade transistor to the SRAM cell to do this so-called rate decoupled cell design. So the idea is that we turn on the additional read VRLAN, and here if we have both, so for example, in this case, you will see that this discharge path is disabled because the data we stored here is 0. Then there's no discharge current at all. But if the data stored here is 1, then we will have a discharge current. So we can still count the discharge current amount on the bitline, read bitline, to do the computation. But here we will not disturb the data stored in the SRAM cell. The reason is that here this cascade is attached to the, this storage node is attached to the gate of the cascade transistor. Therefore, the current flow here will not impact the voltage potential on the gate. And finally, if we add 2 additional cascade transistor, we can do this so-called transposable operation. If we want to do the training, for example, we need to do feed-forward propagation and also backward propagation, then we can enable the computation both in the vertical direction and also the horizontal direction if we exchange the input and output direction. So this is also doable for this transposable operation. So here are just some examples of the SRAM cell design to enable the computation. There could be many other variants as well. And in the next, I just want to have a quick summary for the recent prototypes reported in the literature. So in the recent major circuit conferences, like VLSI and SCC, many groups reported the SRAM implementation for the computing memory. So here I just want to summarize some of the key features. I won't go into the details of the table, and you can refer to the individual papers if you are interested in the details. So here, as we see that the technology node gets scaled in the recent years, and the latest demonstration was from TSMC in SCC 2020. with a 7 nanometer FinFET process with the 8 transistor SRAM cell. And this is a subarray size. And then the input weight output precision are supported in those designs. For example, the TSMC design support 4-bit input, 4-bit output, and 4-bit weights. And then they support different kinds of algorithms, including those convolutional neural networks. And finally, I just want to quote the number, the energy efficiency here in terms of TOPS per watt. And here, because they support different precision, we have to normalize the energy efficiency to be 1 bit by 1 bit MAC. And 1 bit MAC equals to 2 operations. One is multiply, the second one is accumulation. So here the numbers could be very high, as high as like more than 5,000 TOPS per watt for doing 1 bit by 1 bit MAC operation. And here is another table because there are so many demonstrations. So here, this is a continuum table. I will skip this one. So let's go through some of the designs in more details. And this was one of the earliest demonstration of the SRAM-based computing memory. And it's a collaborative work between my group and Professor Mengfan Chang's group from National Tsinghua University in Taiwan. And here we use a split 6T SRAM cell compact design rule from the foundry. And here we initially just supported a binary neural network or XNOR net. And because, if you binarize the weights and the inputs, then the multiplication becomes XNOR operation. And here are some more features of this design. So basically we use a split gate. Therefore we have the VRLAM and VRLAM bar to increase the sense margin from the bitline bar. And here we do need to care about the rate disturb. If the bitline decay to a low level, then the data that's stored in the memory cell could be disturbed. And therefore we have to make sure the VRLAM voltage is lower than the normal memory access mode. For example, if in normal memory access mode, you use 1 volt for the VRLAM voltage. So here we use like only 0.6 volts. And then in the following year, we improved the design by employing this twin AT SRAM cell. So this completely get rid of the disturb problem by adding 2 more transistors per SRAM cell. And here are some features of the chip. I will skip the details, but just want to highlight the schematic of this cell. So basically here, those are the 8 transistors SRAM cell, and we have those cascades as a rate path. But here we want to implement a 2-bit weight. So here a straightforward design is to size up the transistor W over L of this MSB cell as twice of the width in the LSB cell. So here when we discharge the bitline, because the transistor size is twice, so the discharge current is proportional to that. So here we'll get 2 times of the discharge current from the left branch, which is MSB. And then this can naturally implement the significance of the MSB and LSB cell by the current that we discharge from the bitline. And remember, the computation is done by the current summation on the bitline. So the amount of current we extract from the bitline is proportional to the computational result. And we will skip some other details of the design, but one of that is the 2's complementary coding for the negative weights. So, in the neural network model, sometimes we have the negative weights, and we need to use the 2's complementary code to deal with that. And then this is the TSMC's demonstration in the latest technology, like 7 nanometer process. So they use the similar design principles as our design in the previous slide. It's an 8 transistor rate decoupled foundry SRAM cell. And I would say the principle is very similar as the previous design, but TSMC has the latest technology, so they can get the most impressive performance. For example, the throughput and the energy efficiency could be very high. This is for 4-bit by 4-bit MAC. It's like 300, more than 350 TOPS per watt. That will translate to more than 5,000 TOPS per watt if we normalize that to 1-bit by 1-bit MAC. And here are some new features of this particular design from the TSMC. So here it supported 4-bit weight. So that means we have to use 4 columns to represent those 4 bits. Therefore, at the end of the column, we need to reconstruct the significance from the MSB to the LSB. So here, unlike what we did earlier by sizing up the transistor to be proportional to the weight significance, here what they did is to use this capacitive DAC array to do the charge sharing. And here you see the MSB, in this case, has 8 times of the unit capacitance at the end of the column. So therefore, it can increase the significance by 8 times for the encoded MSB weight. And this is also another feature of this design. That's the so-called analog shift and add before the digital conversion. So here we're going to redistribute the charges according to the significance, and then we will do the ADC after the charge sharing. So that means we can do the analog shift and add between the before the ADC. All right, so here are some summaries of the SRAM-based computing memory, and we believe this is a mature technology and with a state-of-the-art availability at the foundry, like 5 nanometer today, and it shows impressive energy efficiency. However, the SRAM suffers from one particular problem, that is the leakage. So if you look at today's processor, half of the leakage comes from the SRAM standby mode. So this is one of the challenges we are going to address in the following section using the number-level memory. And SRAM could be compact, but if we want to prevent the rate disturb, well, we may want to lower the VLAN voltage, or we may switch to the 8-transistor SRAM rate decoupled cell. And foundry actually typically offer both 6-transistor SRAM and 8-transistor SRAM in their memory compiler. So we can directly use that, but we have to modify the peripheral circuits to support the parallel access. Because in the normal memory design, then you can only activate the memory array row by row. But here we have to activate many rows at one time. And also we have to use the ADC to do this analog to digital conversion. So we have to modify those peripheral circuits. And if we don't use foundry's SRAM compact design rule, then we can handcraft the SRAM cells by manually placing the logic transistor there. But if you do that, then the cell layout could be increased by 2 times to 4 times, depending on the logic design rule. So normally in older technology nodes, there are more flexibilities to modify the design rule and modify the bit cell layout. But in more advanced technology nodes, like 28 nanometer or beyond, foundry typically does not allow the designers to make any changes to the memory array. All right, so I will stop in a while in case there's questions. If not, then I will move on to the second section, that is RRAM-based implementations. So here we see some challenges of the SRAM. So let's switch to an emerging technology called RRAM. So first of all, what is RRAM? It's short for resistive random access memory. Essentially, it's a variable resistor, and the device structure could be 2-terminal resistor with a sandwiched structure, let's say a metal oxide sandwiched between 2 metal electrodes. So oxide, nominally insulating, but if you apply large enough voltage, then it can break down the oxide by creating these filaments with oxygen vacancies. Therefore, the current can flow. Then the device resistance switch from an insulating high resistance state to a conductive low resistance state. And on the right-hand side, we show the typical current versus voltage IV characteristics of this RRAM device. So if you start with insulating high resistance state, if you apply large enough voltage in the positive side, then you can set the device from high resistance state to a low resistance state. And then if you reverse the voltage polarity to the negative side, then it can switch back from the low resistance state to the high resistance state. So what could be the benefits using the RRAM compared to the SRAM? So first of all, as a same technology node, the RRAM could be much smaller. So we just need one transistor, one resistor, compared to the 6 transistor or 8 transistor SRAM. And also the RRAM could implement multi-bit per cell. For example, we can encode 2 bits per cell in one device by changing the conductance or resistance levels. For example, if we have 4 resistance levels, we can encode that as 2-bit data. But for SRAM, one SRAM cell can only be binary. You can store only 1 bit per cell. So from the integration density point of view, RRAM could be higher, especially at the same technology load. If we can hold more than like 100 megabytes parameters, then we can have almost all the weights on the chip for most of the image classification model. So this could eliminate or reduce the off-chip DRAM access. And also another key advantage of the RRAM is that it's one of the non-volatile memory. That means if we power off the chip, the data is still there. So this is unlike SRAM. If you power off the chip, then your data is gone. So here, then you can enable this dynamic power gating or instant on and off operations, especially attractive for the edge applications. For example, in most of the time, the sensor load for feature extraction, for example, then is in the sleep mode. Then you can power off the chip. Then your model, your neural network model, still stored in the RRAM. And once you receive some awake signal, then you can start the engine, and then the chip can do the inference right away. So you can save the power during the standby mode for most of the time. And also, RRAM is compatible with the CMOS technology, and we can do multi-tier stacking and potentially. So RRAM has been invested by the industry for more than 10 years now, and it's becoming technologically mature with foundry availabilities. For example, TSMC is offering the 40-nanometer RRAM and in their foundry, and also Intel has 22-nanometer RRAM process as well, and then many other vendors providing foundry, including like Wenbang in Taiwan, Sony, Panasonic, and so on. And here again, this is a summary of the recent demonstrations using the RRAM technology for building the computing memory chip. I will skip the details, but I just want to highlight a few designs. The first one was from, again, National Tsinghua University, Professor Mengfan Chang's group. And this was a 1 megabit RRAM array at 50-nanometer process, and it's 1 transistor, 1 resistor design. And here there are some key. I will skip the performance, like the the energy efficiency and the latency and so on. So I just want to highlight some of the design features. So one design challenge was RRAM is that because now we can turn on many rows, then the current would be large at the end of the column. So we can scale down the current by a current mirror at the end of the column. So here we have a downscaling, which is some current translator for the MSB column, the LSB column, and then we can use different sizing for those transistors to copy the current proportional to the significance of the column. So this is one design feature from this paper. And then in the following year, the same group reported a more advanced 22-nanometer RRAM and computing memory macro, and this has increased the capacity to 2 megabits, and the subarray size is like 512 by 512, and again it's use the tooth complementary coding for the negative weight, and also it has demonstrated like a reasonable accuracy for those CIFAR data set using the ResNet 20 model. So this is one of the state-of-the-art design from National Tsinghua University in Taiwan. And my group, in collaboration with Professor Jason Seal's group from Arizona State, we taped out a design using Wenbang's 90nm RRAM process. And this is one of the vendors from Taiwan offering the RRAM process. And in our design, of course, our technology load is older than the previous paper. However, there is one advantage in our design that improves the throughput. So in the previous design, only 9 rows can be turned on simultaneously. And in our design, we can turn on all 128 rows simultaneously. Therefore, the throughput could be higher and the energy efficiency could be higher. But we do see some challenges in the accuracy, especially for CIFAR10 data set, and we discuss what causes the degradation later. And this is our implementation. We use 2 RRAM cells in adjacent to encode the positive and negative weights, and also complementary input for the VRAM bar for the positive and negative input. So essentially, this can also implement the XNOR operation for the binary neural network. And then at the end of the column, so we convert the current through a pull-up PMOS transistor to the voltage at this sense node, to be sensed node. And this node will be attached to a FlashID with actually 7 voltage mode sense amplifier. So we can have a FlashID readout to convert the data to 3-bit output. And also, another new feature reported in our design is that we explore the multi-bit per cell. As we discussed earlier, the RRAM could encode 2-bit data in 1 resistor. So the way we do that is to manipulate the conductance of the resistor. So here we program the conductance into 4 levels, linearly proportional to the weight value. And here we need to do some so-called write and verify to tighten the distribution. So this is measured from the array. And here this is a CDF, cumulative distribution. So here initially after the programming is very tightened, but as time goes by, there's a challenge. We do see the relaxation effect. That means the conductance will change after some time. And as the time goes by, you see the distribution spread out. So this could bring some challenges in the inference accuracy. And I will skip other details of this design to support this 2-bit weight implementation. And recently, my group at Georgia Tech signed a deal with TSMC. So TSMC offered us a 40nm process for the RRAM implementation. So here, this is the first generation chip we designed with the TSMC's process. And here are some new features we added, leveraging the experiences from our past tapeouts with Wenbang. So here, I'll skip some of those details, but overall, this is a block diagram of the design. So we have this macro 128 by 128 array, and then the peripheral blocks to handle the high voltage programming, and also the verification and the ADC reference generation, and so on. And then the digital blocks will handle the input-output encoding, and then the accumulation for the partial sum, and the reconfigurable precision. So the white blocks basically are synthesized, and then the gray blocks here are manual design. So essentially, this mixed signal mode design. We have to integrate that at the very end. So here are some new features of the design. I will skip the details, but I just want to highlight one particular feature we think is important. So if you imagine your neural network model is stored on the chip, and then this could be a potential, there could be potential security problem, because if someone can read out all the memory contents, then basically the adversary could reverse engineer the neural network model given the weights. And the model is valuable because you spend maybe weeks to train the model with clusters of GPU. And if you deploy the model to the inference chip and someone get access to the chip, then he or she can reverse engineer the model. So here the basic idea is to encrypt the model, but here we still want to preserve the parallel computation. So it's unlike the regular encryption. So you read out the data row by row, and then you decrypt the data. So here we want to do the computation in parallel. So here the key is applied to the input instead of the encrypted weight. So this is a very simple XOR cipher. And only with the correct key, then we can enable the correct row to do the computation. So here we found out we don't need to encrypt all the layers because in the neural network model, some layers could be more critical. In the ResNet kind of configuration, because there are some bypass, so you don't want to encode the. If you ignore the bypass, then you may still pass some information from the shallow layers to the deeper layers. So we have to find the critical layers to encrypt. For example, if we encrypt layer 2 and 5, then under the random attack, so still the accuracy could be very low. That means the adversary could not reverse engineer the model. So on the right-hand side, we show some performance metrics of this chip. I will skip the details due to the time limitation here. And finally, the chip is capable of the on-chip verify and on-chip reference generation. And we have tested it under high temperature as well. So the chip is functional. And then the accuracy, however, suffer from some of the variations we see from the chip measurement. I will go to that point in the next. So here, this is a quick summary for the RRAM-based design. So here, the RRAM could be more compact, typically about like 2 times to 5 times higher density than SRAM as a central load. And RRAM could further be tuned into multi-level. Therefore, we can have higher density, but it may suffer from some of the device non-ideal effects like relaxation after programming and the retention at higher temperature and so on. And also RRAM faces some challenges like high programming voltage. We need to have like 2 or 3 volts to program the cell. So this needs some high voltage generation. And lastly, there's a scaling challenge for RRAM. So as we mentioned earlier, SRAM is available at 5 nanometer process today, but the state of the RRAM is still available only at 22 nanometer from TSMC and Intel. So we believe that this could be a sweet spot for some low-cost edge platforms. If you care about the cost and if you care about the lifetime of the battery, then probably the 22 nanometer with the number of memories like RRAM could be a sweet spot for the design for those edge inference chip. And next, I will discuss some of the general challenges we face for this kind of chip design. So first of all, the ADC could be a bottleneck in the area and power consumption. So here we see that the power breakdown, like more than 80% of the power is from the ADC. And also there could be a challenge of the area of the ADC because those RRAM cells could be very compact. So area for the ADC could be much larger than the pitch of the memory cordon. Therefore, multiple cordons may have to share the ADC. So that means we have to use mux here to do the time multiplexing. This will reduce the parallelism. Ideally, we want to read out all those cordons in parallel, but due to this sharing, we have to use different time cycles to do the readout. And of course, there could be different choices of the ADC, and then here we just showcase FlashID versus StarID. You know, FlashID is like you have many comparators, and then you have different references. So your voltage at the end of the cordon could be sensed in one cycle, and then you could convert that to the binary data after the encoding. And then the StarID thing is to use a star logic. So basically, we have only one comparator, and then we can dynamically tune the reference by comparing the voltage with the reference. So there's a trade-off between the area, power versus the latency. So here we did some estimation on those metrics. So here are the key conclusions that if we need to have higher precision, like 4-bit or above, we prefer to use a StarID to balance the power consumption versus the latency. And this is a variations challenge, as we mentioned earlier. So for end compute, we suffer from variations and noise. That means here we may have the cell-to-cell variations and also the transistor mismatch for the SIM or for the ADC could bring degradation of the computation accuracy. And here we program the RRAM cell and try to tighten the distribution. But as you can see that we cannot get a perfect vertical line here. So we have to deal with those variations. So here, one idea is to retrain the network model because the variation could be unique for each chip. So we cannot apply the same model for all the chips. If we do that, then different chips may respond differently. For example, the same image, then this chip may tell this is cat, the other chip may tell this is a dog. So one way to deal with that is to fine-tune the model parameters to adapt to the variations of each chip. Of course, this will bring some overhead with the testing, but we can do that. So here we show the Monte Carlo simulations for the offset of the ADC output, and we use that as the statistics to do the retraining of the neural network. So that means after retraining, then we can recover most of the accuracy loss due to the variation. In other words, the model could be unique for each chip. And lastly, there's a challenge for the RRAM technology today. So still RRAM has high resistance, has very low on-state resistance and high rate voltage. So this could bring the overhead in the, for example, the ADC area, max area, and also high voltage is to use the level shifter to change the voltage domain from the logic power supply voltage, for example, 1 volt, to the high voltage domain, maybe 3 volts. So here we just did some estimation. If we can increase on-state resistance by 10 times and reduce the right voltage from 3 volts down to 1 volt, then we can get the benefit of the write energy and read energy and so on. And the last topic here is to look at the monolithic 3D integration. So here the idea is that to have two-tier design. For example, the RRAM array, as we mentioned earlier, we need high voltage. So probably we have to use older technology load, which could sustain higher voltage from their I/O transistor. But for the peripheral circuits, we could scale that into more advanced logic load because we don't need high voltage in those logic transistors. So here we show a partition of the design into 2 tiers, an RRAM array at 40 nanometer on top, and then the logic at more advanced node in the bottom tier. So we did some practice using a 3D compiler designed by our collaborator, Professor Sankuling at Georgia Tech, and we practice the design for large-scale 2.4 megabit RRAM tile design. It has a hierarchy from subarray to PE to the whole chip, and we use a mixed signal design flow for the physical design. So this is what we get from the synthesis. So here in the 2D baseline, so everything is on the 2-dimensional space. So we have the RRAM technology, RRAM array, and then the peripheral circuits, like the level shifter, max, ADC, and then the digital control. But if we partition that, we can have the RRAM array at the top. So this is the top tier at 40 nanometer process. So the RRAM and high voltage transistors in the max and level shifter. But then down to the bottom tier, we use 16 nanometer process. And here we have ADC and digital control in the bottom tier. And then we can have a balanced area between the top tier and the bottom tier, and then we can further scale the technology in more advanced node. If we stay with 40 nanometers, then the peripheral circuits also need to use a 40 nanometer process in the two-dimensional space. Then this will limit some of the scaling challenges for the RRAM technology. So we did some PPA analysis, performance, power, and area. Due to the time limit, I will skip the details. But the basic advantage for the 3D design is that the energy efficiency could improve by 4 times, and the chip footprint could be decreased by 50%. And of course, for any 3D design, you may have the concern about the heat dissipation, so the thermal problem. Because you have multiple tiers, then the heat could be more difficult to dissipate. But from our analysis, from the thermal map analysis, we found out that the temperature increase due to the stacking could be moderate. Therefore, the heat dissipation is not a big issue, at least in this particular design. And finally, I'd like to quickly summarize and give an outlook. So here we talk about the computing memory as a new computing paradigm. So this could save the intermediate data movement on chip for those hardware acceleration for neural networks. Therefore, we can improve the throughput and energy efficiency. And we believe that SRAM could be a mature technology to be implemented at the latest technology node. And this could achieve the best performance. But if we want to deal with the leakage power for the standby orphan applications, then we may have to switch to the non-volatile memory solutions like RRAM. And for both SRAM and RRAM-based design, we may face some challenges in the inference accuracy degradation due to the noise and variations, as we mentioned earlier. So we may have to do some like a retraining of the neural network model to accommodate those variations. And RRAM technologies still face some challenges, such as high rate voltage and low on-state resistance. And we believe that if we can take the benefits of the RRAM together with the advanced logic, then we can unleash the full potential for the computing memory. So the idea is to do the monolithic 3D integration. That means use RRAM as a top, and then use the advanced logic as a bottom. And finally, my group actually has open source a simulator to benchmark different implementations like RRAM, SRAM, and also other emerging technologies like a ferroelectric field effect transistor FEFET or MRAM magnetic and emphasis memories. So this is called NeuroSIM framework. So we can basically evaluate the performance for implementing any arbitrary neural network on chip. And this is interfaced with PyTorch. So we can define your architecture in PyTorch and run the inference, training on inference accuracy, considering some of the variations. So we report the accuracy under the variation or under the context weights or context input from the framework. So this is a GitHub link for the tool. And with this, I'd like to thank all my collaborators in the research and all the funding agencies to support the research. I'll be happy to take some questions. Thank you.
All right, thank you so much, Dr. Yu. Very exciting talk. Okay, if you have any questions, please unmute and say your name, ask the question, or send it into the chat.
Hi, my name's...
Go ahead.
Oh, hi, yeah, my name's Dan. Thank you, Professor Yu, for the talk. One question I had was about sort of the overall architecture and picture of these in-memory computation. It seems like the arrays that were being used are maybe 64 by 64 or 128 by 128. And do these reside sort of on the main CPU chip in an SRAM section, or are they in a DRAM chip, or you're just wondering how this fits in? Because it seemed like there's a lot of peripheral circuitry for sort of ADCs and the level shifters. And I just wonder, so how that all fits together.
Okay, got your point. So first of all, what I mentioned here today is all embedded memories. That means they're on the same chip with your logic process. It's not a DRAM or it's not flash. memory. So it's on the same logic process with your processor. But here we are not doing the conventional processor design where you have the caches, SRAM caches. So here we are doing more like domain-specific accelerators. Therefore, you may have a like a RISC-V as controller, but then for the most of the area, we should design those PEs, processing elements, with those memory macros with the peripheral circuits. So the array efficiency could be low from the conventional memory array efficiency perspective. So you have some memory array like 64 by 64, 128 by 128, and then we have many peripheral logic surrounding that. So the array efficiency could be lower than the large memory bank, and you have a minimal logic. So then here the design is different from the conventional memory design, or it's different from the conventional processor design. So this is a new design approach. And but to address your question, yes, this is the embedded memory on the same logic process.
I see. And are you using, is the memory that's being used in the 64 by 64 array, is that storing the weights for the neural network or the inputs, or? So
oh yeah, that's the point. So this is for weight storage. So here we try to do the weight stationary design. All the weights are stored in those memory. And then of course you may still have the input and output buffer to store the input and output feature map. Those could be conventional like register or even SRAM to store that. But we believe that most of the data should be, the weights should be stored in those memory without moving around.
Yeah, okay. And then this whole, thank you.
We have a question in chat. They're asking, do we need the buffers for the RRAM architecture? Because the current flowing through the RRAMs, basically, can that disturb the state or not?
Do we need a buffer? So we need buffer, after output to store the output data, like your intermediate partial sum. For example, the previous question, right? We only have like a 64 by 64, 128 by 128, but then your neural network model, for example, some of the flicked layer could be 1,000 by 1,000. Then we actually need to partition the matrix into multiple subarrays, and then we do need the buffers at the end of each subarray. After ADC, we need to use buffer to hold those data, and then you go through maybe the digital adder tree to reconstruct the final sum. So if you ask the buffer, then we have buffers there. But within the memory array, we do not have buffer. And if you talk about the disturb on the R1, it could be due to the stress voltage. So that's why we have to lower the stress voltage on the R1 to make sure the data will not be disturbed after a consecutive read operation. But if we use low enough voltage, then this should not be a big problem for the R1 states if we use like a very low voltage to read. So we don't need like an additional buffer for the data in the R1 array. We hope the R1 could be like stable over time.
Okay. And I have a follow-up question on that actually, because now it seems like the array has to be kind of reprogrammed for actual larger models. So what is the overhead of the programming latency for RRAM versus SRAM now?
Okay, so perfect question. So SRAM write is pretty fast, right? Like 1 nanosecond. And the RRAM write latency is typically in like hundreds nanosecond, even sometimes maybe microsecond. So it's much slower than the SRAM. So that means we do not prefer frequent reprogramming. And if we can have large enough capacity of the RRAM on chip, if we hold all the weights on chip, we don't need to reload the weights. Then we can use it as inference chip. We just do it one time, and then we just read it. And of course, if the chip capacity is limited, we have to, for example, only hold half of the model. Then you process the first 6 layers, and then you refresh the data. Then you load in the second 6 layers. Then it will cause some delay in the overall processing if you do that. And also that will cause some endurance problem. Endurance means how many cycles you can write the data. So we want to avoid those scenarios. So ideally, if you have a tiny ML model, tiny machine learning model, and you can store all the model on the RRAM array, then you don't need to reprogram it. Of course, maybe after some time, then you want to check if the data is drifted, then you can fine tune a little bit, but ideally we don't want to change the data once we program it.
Yeah, that makes sense. Any other questions from the audience?
Yeah, I had one more question. At the end, you mentioned the monolithic 3D integration. And what I'm wondering is, if we have multiple chips for the ADCs and the RRAM array and et cetera, maybe I'm misunderstanding it, but presumably we're going to have to be shuffling data around between the chips. And I guess, does that not defeat the purpose of having this compute in memory?
So here, when we talk about the monolithic 3D integration, is a very fine pitch 3D integration. So the data only move vertically, not like you travel a long distance horizontally. So then we still try to make the data, data flow, local processing with the data flow. So we don't want to have the data travel long distance. So this won't be a big problem. And for the data transfer, vertically only like hundreds nanometers. Yeah, the precision assay is pretty small if you use a conventional or like a metal weir between the metal levels. Then the precision assay could be very low.
Yeah. Okay.
Any other questions? All right, if there's no other questions, that's it. Please join me to thank Dr. Yu for class time. And see you all next week.
Thank you.
Thank you.